Now, okay, I have to start afresh. Um, what I was telling about, talking about in the previous session, that that this mu3, so not just a minute, that this mu3, the measure of skewness came out to be having value 0 for our given problem. And for positively skewed curve and negatively skewed curve, respectively, the values of the skewness will be either greater than 0 or less than 0, as the case may be. Now, the next discussion is about kurtosis, and I told you in one of my earlier classes that kurtosis is the measure of pickedness of the curve. The normal curves can have three different types of shapes. One is called the highly picked curve, as it is shown by the blue colored figure, and then we have the moderately picked curve, and then we have the flat curve. Like this flat curve is not actually like this, because you see that I have drawn the picture, I have taken the copied the picture from Google, and Google correctly didn't show the diagram. Actually, the flat curve looks like this. This is actually the actual form of the flat curve. It is symmetric, but it is flat. Peakness is not there. One another point which I have observed in this particular image is that this is not correct. Okay, because if I draw a normal curve of this shape, then we know already that capital X, the horizontal axis, is actually the asymptote to the curve, and therefore the tails of the normal curve never touch the x-axis. They touch the x-axis either at minus infinity or at plus infinity. So the diagram is not appropriate, but then probably it may be the case due to the fact that nobody can draw the actual normal curve in the diagram using software, because you see that to do so you need to get hold of infinitely many values, but my space in the computer program is limited. It is giving me limited space. So probably they have considered certain values, up to certain values. Maybe this is -3 and maybe this is +3. Okay, so finite number of values are there, and therefore these points have touched on the x-axis. This can be the reason for which the diagram is like this. But actually, if I talk about the normal curve, they never touch the x-axis. Okay, so from where do we get this kind of scenario? Say, for example, to understand where kurtosis appears in the statistics, suppose in the month of in the coming month, somewhere in the middle of November, say, for example, just hypothetically assume that you are analyzing the situation of 2021, situation of COVID-19, which have made a disaster in 2021, which is now making disaster in 2021 in our country. And you have already started collecting the data of the COVID affected people of say of our country, and you are picking the sample from various states. Various states of the country are the different samples we are talking about. Suppose your starting point is January 15, 2021, and suppose your last date of taking the observation is, say, for example, October 31st, 21. Now what, and you have considered the condition of three different states. I'm drawing, for the sake of better understanding, I'm drawing another curve like this. Let us not consider this this green colored curve, because I don't think it is a flat curve. Okay, this picture is not correct. Instead of this curve, you can consider this one. This is the flat curve, although my drawing is not good. Suppose this particular picture shows the statistics of the COVID affected people from January 15, 21 to October 31st, 21 of three different states. Suppose this is the condition of this is the curve of West Bengal. This is the curve of, say, or not this one, the curve of Assam. And suppose this is the curve of, say, Tamil Nadu. So what you observe that in each of these three states, the number of COVID affected people gradually increased, reached its peak point, and then it gradually decreased. Okay, in every state this happened. That was the trend we observed. But in case of West Bengal, the number of COVID affected people reaches its maximum frequency at this peak point. This is the peak point of Tamil Nadu, and this is the peak point of Assam. Say for example, now all of these curves are normal. Now we want to study which curve, what is the measure of these three different curves. Okay, so we want to study how much they were peaked, how much they were flat. Okay, and how much they were between flat and peaked. So that quantification is done by the measure of kurtosis, where also we take the help of moments. So when we actually, my point is that when we try to compare different normal curves, then this measure of kurtosis actually helps us in our comparison. Kurtosis is also measured. When we want to measure kurtosis, we also take the help of these moments. Okay, so as you can see over here, that this mu4, this is the moment about the fourth moment about mean. Okay, so we need to calculate this fourth moment about mean, which is denoted by mu4, and sigma as well is the standard deviation, which we have already calculated. Now again we have to consider the theorem where this fourth moment about mean has been expressed as expressed with the help of the different moments about origin. Here it is fourth moment about origin, here it is third moment about origin, here it is going to be second moment about origin, first moment about origin, and this mu4 is equal to the first moment about origin. You already know that mu equals to mu1 prime. So we have noted down all the things over here, and then I have simplified the things a little bit, and I have tried to note down these moments in terms of their actual representation with the help of expectation. But as you know that there is a difference between mu r and mu r prime. Remember always that mu r, if you're talking about mu r, then we have to calculate this one, and if you are talking about mu r prime, then we have to consider this one. Okay, that means what? It is the special case of that, because in this case we can write it as ex minus 0 to the power r. So therefore, since you are interested in mu4 prime, mu3 prime, mu2 prime, mu1 prime is same as mu. So we have noted down these as expectation of x to the power 4, expectation of x cube, expectation of x square, expectation of x, and so on. Now we have the probability chart with us, the probability chart on which we studied the measure of skewness. That chart I'm talking about. We have the chart with us. From there, we can calculate the probabilities, the expectations accordingly. So I have shown here some. I have tried to show to you something over here. I have done it for the sake of your understanding. Just let me scroll down a little bit, and then you'll get to see. See, for my calculation, I have made a chart like this. You have to do it by yourself also. That I have considered all the values as it is given in the problem, And I have tabulated all the probabilities, which are nothing but the relative frequencies you can consider. Now, to calculate expectation of the random variable Ex, we need what? Let me try to write so that you can understand it well. So for Ex, we need this formula, isn't it? We need summation x fx, for which I have prepared this particular column. For Ex squared, we need summation x squared fx, so this column. For Ex cube, so we have this. And lastly, for Ex4, we have this. Now you see that all these three columns have been written and have been calculated. The values have been found. And as you can see, the total probability here in this case is 1. All the totals have been found. These totals are actually the summations I'm talking about. Okay. And after that, let's go back. Let's scroll up. We have taken the help of these things. We have taken the help of these results, and ultimately the values have been put over here. All the values have been put over here that has been obtained from the chart, which is mu4, which helps you to calculate the mu4. Sigma has already been calculated. So we have put the value of sigma over, and you know that sigma was having the value of sigma square was 1.45. And therefore sigma 4 is nothing but sigma squared multiplied by itself. So we have written 1.45 multiplied by 1.45, and which is equal to 2.59 approximately, which is equal to 3. Now, how do you know, how can we know that the calculation is correct? Let us try to find it out whether my calculation is correct or not. Okay, we already know that the curve on which, the problem on which we have applied our formula, this particular problem was a distribution, the probability distribution I'm talking about was actually symmetric, whose skewness measure came out to be 0. Now, if we have a symmetric curve, what sort of kurtosis we are going to have? Now, in the kurtosis measurement, all the curves are symmetric. Okay, but I cannot say from the problem whether my curve is moderately skewed or was highly leptokurtic, or sorry, whether my curve was moderately peaked or highly peaked or flat curve, that I can't say from the figure itself. Okay, it is not possible to say the thing from the figure. Skewness, whether it is positively skewed or negatively skewed, can be visualized, can be you can give some sort of conclusion by looking at the picture. But regarding the kurtosis, you cannot put your comment like this, because we do not have other curves so that we can compare. The only way to find it out is to measure the kurtosis. And it is said that if we have a normal curve, normal or mesokartic curve, the value of measure of kurtosis will be exactly equal to 3, which is the fact obtained in our case. For leptokurtic curve, we get the measure of kurtosis to be something greater than 3, and for platykurtic curve, we get the measure of kurtosis as something which is less than 3. So we can note down the things in some other way also. What was the measure? What was the notation that we used to calculate? Alpha 4 was the measure. So in this case, you can write it in the following manner, that if we have a mesokartic curve, then your alpha 4 is equal to 3. Okay, that is, which implies that alpha 4 minus 3 will be equal to 0. if we have a leptokurtic curve, which is where alpha 4 is greater than 3. So in this case, you are going to have alpha 4 minus 3 is positive, and for platykartic curve, we are going to have alpha 4 minus 3 less than 0. So getting a moderately peaked curve in the actual case, in actual system, is very ideal scenario, which doesn't happen at all. The problem which has been given to you is a very manipulated problem. We already knew that if we set the values like this, if we set the values like this, I mean, I'm talking about this one. Let us put the picture in front of you so that I can discuss it well. Just a minute. I'm talking about this problem. This is a very ideal scenario. We know that if we place the probabilities like this, then the value is going to come as expected. We actually expect the measure of skewness to be having the value 0, and we actually expect the kurtosis of having the value 3. So some sort of back calculation have been done, and the result has been presented to you. The question has been presented to you. But this scenario, which is in front of you right now, this is not going to happen in actual case. In actual case, you are going to get some sort of positively skewedness or some sort of negatively skewedness. You are going to get some sort of leptokurticness, some sort of platykurticness, but ideal scenario is very difficult to obtain. It only happens inside the pages of the book. Okay, but to understand those things which are more practical than the ideal scenario, we have to have a good idea, good hold of the ideal scenario itself. Okay, that's just like that. As we see, as we learn in the that all people are good, everybody behave in this particular way or in that particular way. We learn these things in school. Children are taught those things, but in practical scenario, this is a very relative matter. Who is good and who is bad? To some people, it is they are good. To some people, they are bad. Okay, so what is ideal? That this thing cannot be measured in mathematics. Mathematics can give you a pillar, and mathematics or statistics can give you a kind of stick. Now, this is your ideal. This is your ideal point. This is your ideal pillar around which the system works. Okay, and therefore, if you don't know that where your ideal pair is, you know that for ideal scenario, ideal pillar must be there, but you do not know where it is situated. Okay, then we cannot control our society. So by the rules, by the regulations, we set the ideal pillars, and we always try to locate the people who are very near to the ideal pair or who are far away from the ideal pillar. Those the ideal pillar, the people who are far away from the ideal pillar, who make crimes, we take them and put them inside the jail, in the prison. Statistics, this kind of measurement which you have performed right now, giving you some kind of ideal scenario. This is the ideal scenario. Now try to find out your system and try to locate how much your system is deviated from this ideal scenario. So this measure which you have performed over here, the entire measure which you have performed, this measure is telling you two things. One is that some ideal pillar is there. That is the location of the pillar, be it kurtosis, be it skewness. It is also telling you how to calculate the values of the skewness and kurtosis in its ideal scenario. And then it is telling you indirectly that as you now know that your hypothetical pillar is situated over here, now try to study the system around, and with respect to the ideal pillar, the location of the ideal pillar, you try to study your system. Okay, so this particular study is very important, and I think I taking considerable amount of time to make you understand the thing, because this is what is actually done in statistics. So this particular note and today's class is very important. And I'll recommend all of you to go through the videos again and again once I upload them in the YouTube, and try to understand the try to grasp the basic idea behind these facts which have been represented today. And in the last part of the note, in the last part, I have concluded the note with 3 formula, which is written below. As you can see, these formula are actually, you see that giving you the moment about origin in terms of moment about mean. But one thing you will find out over here, that you already have the formula for moment about mean with written in terms of moment about origin. But if you are thinking that we will take this, we will make the site change and then we'll get this particular formula, it's not going to happen. This has been derived in a different way. Okay, the derivation is not actually done. If you change the side and this will come out, it is not going to happen. You have to again perform the mathematical induction process from the scratch to get this particular thing. But I'm just giving you this particular set of formula, this 3 formula, where my cursor is located, just for the sake of completeness. But I shall recommend you I shall ask you to forget this particular set. Just try to remember the original theorem which I showed you in the beginning of the class, first session. So I shall ask you to always remember this result. This is the only theorem, this is the main theorem which is important for you. Now, in the chapter of moment generating function, in the exercise, I'm talking about the John Freund book. In the chapter of moment generating function, we'll get an exercise where this skewness question which we have studied is given. Now, below the problem, I have solved one problem for you from that exercise. There is another problem given in the same exercise of skewness and kurtosis. Try to find out the problem. If you are not able to find out, I will text you the page number later in WhatsApp, and try to do it by yourself. You can, for the time being, you can take the help of Excel, and you can draw the figures, or you can do it by scale and pencil. Doesn't matter, but I am actually interested about the calculations. Calculation is very important. What it reveals is very important. So with this, I'm going to conclude my today's session. Tomorrow we have class in the afternoon session, and there we are going to discuss something else. Okay, I have class with the CSEB in today's at around 1:40. There, I'm not going to discuss this. I'm not going to repeat these things. I'll try to upload the video in the YouTube now, and I'll ask all the CSEB students to go through the video before they come into the class. For them, I'm going to start something else. And if I can finish the topic which will be started in CSEB today, then tomorrow in your class, I'll start something else. But if I cannot finish what I'm starting in CSEB in afternoon session, that will be continued into your class tomorrow. So my point is that before you come to my class, try to go through my video once, okay, so that you can at least know that what has been taught in the previous class. Okay, so with this, I'm going to conclude my today's session. And you don't forget to do the calculation which I am asking you to do. So bye for now. See you tomorrow in our scheduled time.